Okay, so I assume everyone has the files downloaded. So we're gonna start with just like introducing why we're doing this actually in the first place. So please open the performance bottlenecks TOW file. And gonna start by just, yeah, just for me this, yeah, okay. So in this image, what's important to understand, basically performance, because this is the core issue that we want to address here, is to be able to push subs to, having more, dynamic subs, but without having this, laggish behavior. And understanding how a GPU works or how, real-time pipeline works will help understanding, how the solution I suggest is actually working. So on a GPU, and tell me if you already know this, I don't have to recap it, but if you don't, I prefer to explain it. So there's always the CPU, GPU domains when dealing with the real time. Usually what happens on CPU is when, the geometry is built. So the game running like an animated character, we're gonna basically construct or build a geometry on the CPU and then send a stream of data to the GPU. So the communication is using, for example, OpenGL or Direct 3D, which are languages for the CPU to communicate with the GPU. And then when this data is pushed, it's using the PCI Express, bridge that basically will transfer data onto the GPU board. So the GPU board is kind of a, it's like a sandbox, and we want to stay on this sandbox every time basically. We want to run everything there. So because the geometry is built on the CPU and sent every time in touch when we build the SOP, until now, is rebuilding on geometry using the CPU. Okay, and because Search Designer is single-threaded for this, it's gonna use a lot of time. So it's very simple, for example, to see that. If you look at a classic box and just applying a noise onto it, if you look at the time that is spent there, it could be like 1 or 2 milliseconds for something that it's not like super huge. If we push it to just 100, 10, 10, oops, sorry. This, well, already it's impossible to actually make this geometry evolve in real time. So that's the main issue right now that we want to be able to bypass. So here, in this example, everything on top of this horizontal line is happening on CPU, and under it, it's GPU. So we want to crossing this line also has a lot of cost. For example, if you want to analyze an image, analyze a movie top, and detect some blobs, well, all the tops are on the GPU domain. So they're all accelerated by default. So as long as you stay in the top family, it's gonna run shaders, it's gonna run, GPU accelerated stuff. So it's gonna stay on the GPU in the video memory of the GPU. As soon as you want to analyze, well, the blob top is an exception because it's using OpenCV, but in general, it's like this. But if you want to, for example, get a chop out of this top, that's when all the texture is going to be downloaded. So it's going to go from video memory, from the GPU dedicated video memory, onto the RAM on your next to your CPU actually, and it's going to go through PCI Express. And this is, it can be blocking when rendering this. So if we do, then usually we just delay and then wait a little bit to get the data back from the GPU. But if you want to have like, let's say, very tight interaction, that is an issue. So the more we do on the GPU, the better. So the other example is using the transform SOP. So I assume that every one of you know that you never use the transform SOP if it's actually changing every frame. The only reason why you use it is because you're building a static SOP, and then you're going to use this one to do further processing. So just to illustrate this is like we do the exact same transform on a geometry, and by doing this, we're not changing the geometry itself, we're just making it rotate around its center. So the GPU is actually taking care of that instead of changing the SOP. So, you know, the order of magnitude that we have is like the more we have vertices, it could be 1,000 to 1 or like 10,000 to 1. Same for the tops and the chops. So just generating random, like let's say how many channels? It's like 256 channels of animated noise. Well, it's not even animated, but if I cook it once, force cook, then I see like 32 milliseconds. So I cannot even, using chops, I cannot have, you know, like a, you know, fluid or low cost generation of random. And this can be useful when I want to have a lot of different random channels to apply onto a geometry, for example. So even there, it's faster to actually use a noise stop, because the noise can be generated on the GPU. And so the difference is like 400 times faster there. And then it's actually faster to convert that generated top back into a chop to actually have the exact same channels evolving over time. So that's where like downloading a top into a chop is less intensive than generating this chop on the CPU. So it's interesting. So any conversion between top and chop, between that and top, anything between basically top and something else than top is going to cross, you know, this boundary. So the idea is to stay in the top domain and use shaders to actually use those tops to generate geometry. And that's what this workshop is about, is introducing the, or not, you might be familiar with it already, but the geometry shader, which has the unique ability to generate geometry from nothing. Well, not from nothing, but it's going to take instances or primitives, and then you do whatever you want with it. It could be static, could be a static SOP coming in, but then when generating the geometry, it can do that in a dynamic way. So that's how you achieve like a SOP that is dynamic. Okay, any question regarding this? Okay. Oops. So let's close that. Now let's open the second one, GPU pipeline and shaders. Just for the people, because in case, you know, who among you is not familiar at all with the vertex shaders? Yeah, okay. So I need to explain this in order to introduce the geometry shaders. So we're going to open this this file there. I guess most people dealing with shaders, they focus on GLSL top, and yeah, the infamous shader toy. So, okay. So, thing to understand, well, pixel shaders, the way we use it is like they take a geometry, they take a full screen quad as an input. And for every pixel of this full screen quad, it's going to run the pixel shader. So every pixel is going to be, you know, we're going to compute the color, and it's run, you know, all at once. So that's a big difference with the, you know, let's say processing or something. you're applying the same program on every pixel at once. So it's not one after the other. So, if you have looked at shader toy shaders, what you see is basically a rule. It's not a loop. It's just the program that will deal with every pixel in the image, and it's using, most of the time, the location of each pixel in the final image as like the variable that will make the rule give different colors in the end. So that's the very end of the pipeline where every geometry that we want to display on screen is actually happening. So the very final stage. So we're going to see what's happening before that. Before we actually build this full screen quad, before we give the attributes to the quad so we can actually run the pixel shader. So the job of a GPU is basically turn a bunch of 3D information like vertices, how they are joined together and forming triangles, where a camera is positioned so I can have a look at this geometry and what's my, let's say, field of view that I'm going to use. So all of those informations are pure 3D. But in the end, I have a screen. I need to show like a 3D environment on my screen, which is basically 2D. So we need to make calculations to transform 3D models and cameras and angle field of views into 2D locations of triangles on my screen. Okay, so that's this first part is done by the vertex shader. So that's his job. It gets a lot of vertices connected together with the camera information, and then the final result of the vertex shader is this vertex is here on your screen. This other one is here, and that's how we build primitive on screen. So let's see quickly, because it's important to know, I think, if we want to push coding shaders, is understanding the different spaces that we have to go through to go from 3D to screen. So the first space is called object space. So in every case, it's like 3 axes. Well, there's an origin, there's an X, Y, Z, and it's really a matter of, what is the reference? Where is the 0, 0, 0 in my space? So the object space is basically when creating a SOP, this is the space we are in. So a sphere, we're going to say the radius and the center of the sphere. But the center is actually in object space. We don't know yet where we're going to show this sphere in the world. We're just building a 3D model to be used later. So that's what we see here. The teapot is just centered on its origin, and that's the object space. And in a vertex shader, so the same way we have pixel shaders, it has known variables or known information when running the shader. So the P letter represents the object space location of every vertex it's processing. Okay, then we need to display several teapots in the world, like 3 copies. Well, we are still using the same 3D model, but we are displaying it at multiple locations. So each of the copy will have a different world space position. So it's basically the information on a geometry container, the transform and scale and blah, blah, blah. This is basically the world space position transformation that we're specifying. Okay. So in a vertex shader, to go through different stages, it's done this way. So we have the object position as a start. Then we call TD deform, which is a built-in touch designer function that will transform from object space to world space. But it's not finished yet. It's still like, we just changed our reference to be the world origin instead of the object origin. But it's not over yet. We don't display anything on screen yet. So the next space is the camera space, because we look at those geometries from a specific point of view. And this will change where each vertex will appear on screen. So this space called camera space, in this space everything is relative to the camera axis. So it's like shifting everything in front of the camera, basically. And again, to go from the last space we were in, which was world space, into camera space, we use matrices. So it's a way of applying transformation, of changing one coordinate system to another. So I will not go deep in what a matrix is, but just remember that this is the mathematical tool to go from one to another. Okay, then the last one, and this one is interesting, is we actually need to define, we moved everything in space, but we still need to define what do I show in front of me. It's not the whole thing, right? It's just like, I need to apply perspective, I need to show like kind of a cone. It's like a pyramid in space, a section, and I want to show that onto my screen. So the way it's specified is the field of view of the camera and the front, the clipping planes, the near plane and the far plane, which is a setting of a camera. So we are just defining this pyramid where we want to see geometry. And in the end, what we want to do is show that on screen. So the thing to imagine is like we turn this pyramid into a square. So it's like we are morphing it. So the front plane is squishing when it's expanding, and the back one is reducing. And you can imagine how close objects appear bigger than the objects that are on the back. So that's the perspective effect and how it's applied. And in the end, the space we are in is basically a cube in screen space. So this slice, like -1, -1, so x, y represent the x and y of my screen. -1, -1 being the bottom left corner, and +1, +1 the top right corner. And then the last coordinate, z, is the depth. And that's how we're going to decide which triangle is in front of which other triangle when applying depth test. So it's always normalized between 0 and 1. So the bigger this pyramid is, the less precision we have when squishing that back to -1, 1. Okay, and the function for that is TED, another built-in function, camera to projection, and we use the last position in view in a camera space. Okay, so now we have to imagine that imagine the stream of vertices that we built with the SOP, send that to a vertex shader. Vertex shader applies all those transformations and figures out where each vertex is located on screen space. Then the next stage is a primitive assembly. So now we just have like a bunch of vertices. We join them together to build triangles. So it's just geometry for now. It's not even pixels. Then the next stage is to transform those, it's kind of a vectorial information, into pixels. So that's called rasterization. And this is, we don't have control on this process with shaders. It's GPU takes care of that. And by transforming those triangles into pixels, then it's gonna, whatever is computed at each vertex is actually interpolated. So if we compute a color, like a lighting on each vertex, then the pixels in the center of the triangles, they get different shades and then just interpolate between them. So so basically the process is like vertex shader, then rasterization, then pixel shader that handles the pixel colors. And when doing a GLSL top, it's just like this process of building the geometry is hidden, It's just like we draw a full screen quad, and that's what the pixel shader is going to run on. Now, to introduce a geometry shader, that's another stage that basically will get in between the vertex and the pixel shader. So the vertex shader will output primitives. Well, actually, it's kind of outputting primitives. then they can either be rasterized and sent to the pixel shader, or they can go into an additional stage of using a geometry shader. Then the geometry shader will receive primitives. And that's the big difference. It's not receiving just one single information which has no clue what's around it. A primitive is like the whole, for example, triangle. So we know what the size of the triangle is. We know the connectivity eventually of this triangle. So we have a lot more information that we can use in the geometry shader. And it's going to be able to, oops, I'm going to shift here. Yeah. The geometry shader here, so in the middle. We can actually create primitives. So for each triangle, we can generate 2 triangles, or for each, we can change primitive type as well. So we can have like a line as a primitive going through and 2 triangles out. So a typical example is like a particle system. To avoid pushing like 10,000 quads, that's a lot of vertices pushed to the GPU, just push 10,000 points. And then geometry shader receives each point location and transform that into a full screen quad, not full screen, but a billboard to actually run and eventually make the billboard rotate and everything. So that's, I think that's the one used in the palette. Do that. Okay. Something else, yeah, I did not present yet is everyone is familiar with normals, vertices, normals, UVs. You all are familiar with that. I don't need to explain this. Okay. Okay. The thing I need to explain also is, let's go to the shader duo there. The way to create like a pixel vertex shader, kind of a duo, is to go from Phong material, or a PBR actually, and then using this output shader button in the very bottom, you can generate the shaders that actually represent this exact same look, but with the shader code. There is a checkbox for including the geometry shader. So it's kind of a nice starting point to work on geometry shader. If we do that, we'll generate like a Phong GLSL material. And you see the way it's set up is like vertex, geometry, pixel in the right order. Then the thing to remember is, because every shader is feeding the other one. So everyone has inputs and outputs, and they need to match. So when looking at vertex shader, it receives vertices. So we don't define the input because it's a known. It's like those arrays of vertices with P, N that I explained before, and UV information for each vertex. Then it defines the output that will go to the geometry shader in this case by defining the out vertex. So I'm going to send for each vertex, I'm going to attach the color, the world space position, world space normal, and camera index. Then the geometry shader is going to receive this as an input. So it's declaring what it's receiving as an input. And you see here, it's not just one vertex. It's like an array of vertex because each primitive has multiple vertices inside. And then the output would look like what a vertex shader would send to a pixel shader. But here it's a geometry shader that does that. And this shader that we see is basically, let's say, kind of a pass-through shader. So for each primitive, so remember it's running on each primitive, and we actually define here in the header what the type, what the input primitive type is. So it could be a series of lines, a series of triangles and series of points, but I never managed to really make a point input work with the geometry shader. So that's the input, and that's the output. Sorry, the input is layout, the kind of primitive we're gonna expect. Layout in and layout out is the primitive type for outputting. So here we are receiving triangles and outputting triangles, and max vertices means how many vertices maximum I'm going to generate. So the way we generate geometry, or primitive on the geometry shader, is to emit vertices. So create a vertex, and then we're going to call something called n primitive. So I emit 3 vertices in the geometry shader called n primitive, then it's going to create a triangle. So here we have the option of, for each triangle, we can generate 3 other triangles. So that would be, 3 times 3, that would be 9 vertices maximum that I can emit inside the geometry shader. But here we're just receiving triangle primitives and then outputting triangle with 3 vertices. So we don't create geometry, we just recreate the same that we receive. And here it's a loop that we loop in the array of vertices that are contained in the primitive. So primitive contains 3 vertices. We iterate like 0 to 3, and we're just emitting 3 vertices with the exact same information that we got as an input. So it's doing nothing, basically, but it's just a stage we can modify after. So keep in mind that here we still have access to the same kind of input any shader does. So we have access to tops, external textures. So each pixel of an input of a top could control the size of the triangle we're going to pass over. So imagine we could have a grid, and each primitive of the grid is going to look up a different pixel in a video, and then it's going to make it bigger or smaller. And that's basically how we make the SOP dynamic and staying on the GPU. Okay, and then the pixel shader, I'm not going to go into much detail here. It's not necessary, except it received the output of the geometry shader here. Okay. Yeah, just to make sure, let's go in this one. You're all aware of how uniforms are working in the shader? Yeah? Okay, good. So I don't need to explain that. And uniforms, also samplers. So yeah, that's what we're going to use in the geometry shader. So, okay, any question regarding vertex shader, pixel shader, geometry shader? Sorry? Yes. Yeah, this one? Yeah.
Is that just, can be 4, like can be numbers?
The max vertices? Yeah. It's a way of telling the GPU how exponential it's going to be.
Yeah.
Because it has to allocate some video memory to your shader.
Yeah.
So if it knows there are like 10,000 points of the SOP that is running this shader, it knows that it has to, for each primitive, allocate at least this amount of memory to deal with 3 vertices, because here we are multiplying, yeah, exactly. So it's the maximum number. You could emit 1 or 2 or 0 when dealing with each primitive. It's just like a maximum number. You're never gonna, go past. Yeah.
There's no limit.
Well, yes, there's a limit. Usually, it's depending on your GPU. Some of them there are more, but it's not like you cannot go crazy, but still, it would be interesting to see for like a GPU what's the actual limit is. But usually, it could be like for each point you draw a cube, for example. So it's like, well, yeah, because in the end you're gonna have like an array of like a donut or something that is you're gonna emit vertices on your. You could, and that would be actually the most efficient way. But yeah, I never push that way too much because you draw simple geometry like triangles and cubes. Okay, so let's move on. Let's close this. So now let's see more practical examples of geometry shaders. So let's open the simple geometry shader.to. And actually, we're going to start with everything that I said. This nice video that I really like, that with lots of illustrations that recaps everything that I said. So we're going to watch it. Then after that, if you still have questions, feel free to ask. So I'm going to show it.
Hello everyone and welcome to this week's OpenGL 3D game
But the
tutorial, and this week we're going to be having a look at the basics of the geometry shader. So before we have a look at the geometry shader, let's just quickly recap what our shader pipeline looks like at the moment. So let's say that we want to render a simple cube. The first stage of the pipeline is the vertex shader, which takes in each vertex of the model and it processes them individually. The vertex shader gets its input data for each vertex from the VAO, and it outputs the vertex with various user-defined values associated with it. The vertex shader also sets the inbuilt GL position variable for each vertex, and this inbuilt variable tells OpenGL where on the display the vertex should be positioned. At this stage, OpenGL then assembles the triangles from the outputted vertices, or to be more general, it actually assembles the primitives at this stage, and primitives are just the building blocks of what you're rendering. We've always rendered triangles in these tutorials, but you can actually just render lines instead, or even just points. Points, of course, would just be a single vertex, lines would be 2 vertices, and triangles are obviously made of 3 vertices. In this example, the primitive that we're rendering is triangles. Once OpenGL has assembled the primitives and determined where on the display they should be rendered, the fragment shader executes once for each pixel that the primitives cover on the screen. The inputs to the fragment shader are the interpolated per vertex variables, and the fragment shader uses these values to determine the output color of the pixel. So this is the shader pipeline that we've always used in these tutorials, but we can actually add in more shader stages to this, such as the geometry shader. The geometry shader fits in right here, after the primitives have been assembled. The geometry shader then executes once for each primitive, so if we're rendering triangles, it executes once for each triangle in the model. If we were rendering a load of lines, it would execute once for each line, and if we were rendering points, it would execute once for each point. The input to the geometry shader, therefore, is the entire primitive that it's executing for. So unlike the vertex shader, which just has access to one vertex, the geometry shader has access to all of the vertices in the current primitive, and any values that have been assigned to them by the vertex shader. So if we're rendering triangles, the geometry shader will have access to all 3 vertices and the values associated with them. This means that the output variables of the vertex shader are now the input variables of the geometry shader, and notice that the geometry shader inputs have to be arrays, because the input primitive can have more than one vertex, and so there's more than one of each input variable. If you're rendering points, these arrays will actually just contain one element each, because there's obviously just one vertex in a point, but if you're rendering lines, then there would be 2 values in each array, and if you're rendering triangles, there would of course be 3 values in each of these arrays, one for each vertex in the triangle. The geometry shader then uses these inputs to process the primitive in whatever way we want it to, and it then generates and outputs some primitives. The type of primitive that it outputs, how many of them there are, and what they're like, is totally up to us as the programmer. If we wanted, we could use those inputs to generate the exact same triangle and output that, although that would kind of be pointless, and we might as well just not have a geometry shader then. We could, however, process each triangle and output 3 triangles, or 6 triangles, or however many we wanted. We We can even output 0 if we want, so the geometry shader can also be used to remove geometry. And it doesn't just have to output the same primitive type as its input. For example, let's say that we're rendering points instead of triangles. The geometry shader executes once for each point, and for each point it could generate 2 triangles, or maybe 6 lines, or whatever you want. It's totally up to you what your geometry shader does and outputs, and the only restriction is that it can only have one output primitive type. So you can either choose to output triangles, lines, or points. You can't output a mixture. When we generate these new vertices in the geometry shader, we can also give them some per vertex values in exactly the same way that we do in the vertex shader. So we can give these vertices any values that we want to give them, whether it be a color, a brightness value, some distance, or anything else. Just one.
Yeah, that's very powerful in that you can inject new attributes to vertices inside the geometry shader. Instead of going through like a SOP that will inject attribute, you do that inside the geometry shader and add as many channels as you want. So that's pretty nice.
Whatever information about the vertices we want to pass on to the fragment shader. And of course, we also have to set the inbuilt GL position variable for each vertex to tell OpenGL where the vertices should be positioned on the display. And that is the geometry shader's job done. So after that, the fragment shader can just go ahead and do its usual thing with the generated primitives. One important thing to note is that the inputs for the vertex shader come from the VAO. The outputs of in the geometry.
Yeah, there's an example for that. Like, remember, like, if you want to draw wireframes on top of the actual geometry, it's like you have to render 2 passes. Okay, so this is a typical example of inside the geometry shader, because you know the 3 points of the triangles, you know how close we are to the edge. And we can actually create information attached to the vertices that when the pixel shader is going to run, it's going to use this value to know if we are close to an edge or not. And so it's like a very useful, I'm going to show like the actual an actual example using it, but it allows you to draw your geometry plus wireframe in one pass using the geometry shader.
Shader that you can't calculate in the vertex shader because the vertex shader only has access to the one current vertex, whereas the geometry shader has access to all the vertices in the primitive. There are also loads of other cool things that you can achieve with the geometry shader that we'll perhaps look at in future tutorials, but for now we're just going to take a look at some of the basic GLSL code that you need.
All right, so that's, I think it really helps, having a visual explaining how it works. Just out of curiosity, how many of you never played or never knew what a geometry shader was? Okay. 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 So you understand how underused it is? It's not used at all.
Yeah, I do 3D modeling, so it makes sense.
Mm-hmm. And it's really, I think it's so cool. Geometry shader is like, I wanted to find an application for it. So back to the presentation. So yes.
From the video, they said like instead of you can just make the particle like correcting a particle
Mm-hmm.
and just answer the geometry shader just let it as it is.
Yeah.
But you can also do the just particle of the points.
Yeah.
And you can generate some rectangle out of the point.
Exactly. Yeah.
But what's the big differences? I mean, outcome is the same, right?
Outcome is the same than what?
Well, what's going to be different? You can just make just one and then create.
Oh, well, it's faster because instead of sending, it's this flow between CPU and GPU. The more data you send, the more intense it is. It's like when you're pushing like 10,000 triangles.
Okay, so it's going to be the bottleneck between CPU to GPU.
Yeah, exactly. And actually, when building a 3D model, you want to minimize the number of points that you send. It's like a mesh or a polygon. You could have 3 points repeated for every face, or some points shared between faces. So it's always like an optimization that we want to push in real time. So here it's cool because you divide the amount of data by more than 4 because it's just 1 point instead of 4 points plus the connectivity, because even so it's more than 4. So you can send like really a lot of points and not worry about performance. And another example some game use is tessellation. So you send like kind of but it's tricky to use because you need to send the connectivity of all triangles when you send the data, the vertex data. So it's not that super easy to program, but you can actually subdivide on the geometry shader to have more detail. And but let's see. Yeah, the tessellation. That's the thing is, in order for the tessellation shader to work, well, there's a tessellation shader, but the geometry shader can be used to tessellate as well. Yeah. The what? You mean?
As far as I know, touch standard doesn't.
No. And usually it works because when you send the geometry, there's all the connectivity, is already sent as well in a predefined manner. Okay, so one simple example, if we look at this thing, is shrinking every face of a SOP. So if you want to do that with there are SOPs that would do this, but if we use them, it's going to run every face. It's going to recreate the geometry on the GPU, on the CPU, sorry, and do this. Here we can do that. It's actually a nice way of making an object appear or disappear in space. This one, if we look at it, was generated by going starting from the Phong material, then transforming into a GLSL GLSL material, sorry. And then if we look at what's interesting is a geometry shader here. If we edit that, okay. So here we are dealing with triangle primitives as an input, and we are outputting also triangles. And this loop is pretty simple. Here, that's just a way of saying it's great because I've got all the information on the primitive itself. I know where each point is. So I can use this data is available in the array that we saw in the video, the array of vertices. I know I have 3 vertices. So I just use the 3 of them and compute the center of the triangle by averaging the positions. And then I'm going to build an array of the new position of each point of the triangle by shrinking. So I'm using a uniform there and going towards the center of the triangle. So those are my new position. And then in the loop that we saw earlier, well, instead of passing the world space position, so that's why I explained the different spaces. Just so you understand what this is. Pass the new world space position by the array that I use here. And see why I used world space position to change the position. Because I'm not changing the position in object space. I'm changing the position of where it's actually in the world. Yes, and we are emitting 3 vertices. And after that, we are creating a triangle by calling the end primitive function. And each time I call end primitive, it's going to build a triangle from the 3 points I've emitted before. Okay, so that's one example. Well, actually here it doesn't make a difference, to be honest. Yeah, it's more like the origin, if the origin is the origin on the world. Well, we don't use the origin, actually. So that it doesn't make any difference because we're using the 3 points. And so, yeah, in this case, it's not important. Yeah, exactly. Yeah, exactly. Another cool application of geometry shader is cutting geometry. So for each primitive it receives, we can decide if we generate it or not. Well, if we regenerate it or not. Here, this GeoShader has sliders, and basically we define the limit where, you know, those, let's say each primitive will go through or not. So imagine one practical example is, let's say, like a Kinect data, or you have like a big point cloud. There's some, you know, noisy stuff you don't want to see. Well, you can actually get rid of the geometry. You know, it's not just like a far plane for a camera. You're making your SOP lighter by using a geometry shader and removing the triangles that you don't want. And it's super fast by doing that. There's no SOP operator involved, so it's not running on CPU. Okay. Yeah, if we have a look at the actual shader, let's see that. Well, it's a condition. So we're using uniforms to define like a box in space, limit z, x, y, z limits in space, and just comparing each input vertex with those limits and determine if we are outside or not. So we are only emitting vertices if they are inside the zone. So that's how, you know, those some triangles they don't get displayed. Okay, any question for that?
Even when you don't limit the primitive, you still need to write.
Well, actually, could be up. All right. So calling end primitive when no vertex has been emitted is like, yeah, it's not going to do anything, but still it's not necessary. Okay. Yeah, see, it doesn't change the output anymore. Okay. Then something else is, well, remember that we can use external data in a shader. So tops, that, you know, it's the most efficient way of generating noise or generating, you know, data changing over time with lots of channels. So in this example, it's just using tops as the source of positions for my primitives. So if we have a look at this, okay, and this is something that we're going to use a lot later on, is here, you see the actual SOP I'm using, it's a line, but it's a line that is completely static. Okay, the only important thing is the number of points on my line. That's going to determine the number of primitives that is going to be sending to the geometry shader. So the line here is the most, you know, it could be points, but I never managed to send points anyway. But there's very few connectivity. I just want to send primitives. And here, this is, you know, moving, but the SOP is not. So the geometry shader is actually changing the primitives to make them appear at location that are actually specified in this top. And the color is also taken from inside there. So there are a few things very important to understand. Let's open the geometry shader. Okay, so depending on the version that you have, but I guess you all have recent versions. If you don't see anything, it means that you have to change the input layout type from lines adjacency to lines. It's just that this has changed recently, but if you do you all see the thing correctly? Yeah. Okay, good. So here now the input is actually lines. So lines adjacency means in the primitive is not just 2 points. It's 2 points and the neighbors of the the lines before and after. So it can be used to actually know the curvature of the line if you want to use it. So you have 4 points, but usually we just use the second and third one. The first one and the last one is just optional. Here we are putting a line strip with the maximum vertices of 6, so we can eventually create some more points and create some more lines in the shader. Here what we use additionally are samplers, so textures that we're going to use as basically the positions for each of the instances, well, each of the vertex. So positions, colors, and this is important also, is as a uniform is the dimension, the pixel, the width and height of the position top, so we know where to look at. I'm going to explain that. So here, just a recap on the kind of data that we have. So we have 4 points in our line primitive, and P1, P2 are the one that we're interested in the array. So that's why in this loop, we're just considering we are indexing the array, starting at 1 and ending at 2. So that's why we do that. And this thing is really important. So in case you have not used it before, it's an attribute of each vertex. It's the ID of the vertex in the geometry. So they all have unique IDs. So for a quad, I have 4 points. The first one has ID 1, 2, 3, 4. So it's kind of a unique identifier of each point. And that allows the shader to know which vertex it's currently processing, depending on this number. And that's something sent by the vertex shader, actually. Using this number, we're just figuring out where, imagine like each point of the top represents a position. So the first position is top left pixel. After that, it's the pixel right next to it. Then we go from left to right. And well, actually, we start bottom left, and then right, then we go up, then we go right. So we need to know, to have a formula that uses the vertex ID that will tell us where to look in the position top in UV coordinate. So this formula is, we're going to use a lot to actually get the position UV. So position UV represents where for the vertex ID, where I'm going to look here. So for example, there. Okay, then we get the actual position. So here it's very important to use floating points textures. So I guess you're familiar with that. So by default, tops are 8 bits, and they are limited to 0 to 1 range. So if you want to show points and outside this range, it's not going to work. So always change it to 32. And yes, so we have this new position. The color, we actually use the same kind of technique to look up a color. Then here, it's the formula I was explaining to go from object space to screen space. There's actually like this one-liner that goes directly from object space to screen space. So GL position, remember the video, it's actually the location in 2D on the screen. And we call emit vertex. So here, oops, I'm going to do that. So here, that's what we see. It's like we're just going through a line of this top to define the new position of each vertex of the input primitive. And because the ID, each vertex along the 2000 point line increments, in a continuous manner from 0 to 2000, we look up in the texture on a single line. So this is why we have this kind of continuous look. Okay. And then just to show the effect of creating new vertices, here we can decide to create a new point that is slightly further from the point we just emitted before. So by doing that and saving, well, we just inserted new points along the line for virtually free. It costs almost nothing to do that. Then we also have the choice of ending primitives early. So it's kind of a way of cutting through the line, because some lines are, well, the line is actually always closed, so that's okay. Doesn't make a difference. Here, if we want to go from a line to triangles, oops, where am I? Oops, I was inside there. Then we have to change the output type. So instead of line strip, we're going to comment this and change to triangle strip. Here, max vertices equal 3. So we only can emit one single triangle. And if we go back to the end, we can emit like a new point again. And now we need to call n primitive, because we emitted 3 points and we want to create a triangle there. Did I change it? Triangle strip. Don't know why it's not actually emit vertex, emit vertex. Oh, yes, that's true. Just using 3 points. Yeah, something I need to understand there. Why? Well, here I have emit vertex, then another emit vertex, and then n primitive. So it should do this. I don't know why it's different there than it used to be. So I don't know. Yeah, sometimes we had to define it here, but it doesn't seem to make a difference there. Well, it's okay. Let's not waste too much time there. So that would be a triangle displayed. So I have other examples that will show that in effect. Okay. Yeah, there. Well, it's kind of weird. Yeah, it should not be different actually there, but sorry?
If you make the output geometry triangles,
yeah,
you still make n primitives.
Yes. Yeah. But I think if you don't call it, if you emit like but I never tried it. If you emit 4 vertices, it's gonna create like the primitive and discard the last vertex. But anyway, yeah, that's the first time I see that, but it's fine. I just updated my version yesterday. Okay, so here the thing to remember is like, we can actually use tops to define our geometry. to define the location of each point of our geometry. And that's the idea that is behind transforming a SOP into top, because I can get an input top and actually storing each point location into a top, and later on I can reuse this top to do this kind of stuff and to recreate the SOP from those textures. So that's what we want to do. So yeah, I'm getting there.
I think it might combine the saving problem we were talking about.
Oh yeah.
So check the geometry shader itself in Touch Designer and see if that actually changes.
Yeah, that would be an issue if I need to change every time. It's possible that, yeah, line strip, damn it.
Yeah.
So what should I do? It's like do this.
The easiest thing I would think is copy everything.
Copy paste.
and then just-
Oh my God. Really?
Like, you can do
Oh.
Control A and then Control V.
You know, I updated yesterday to make sure it was working. Yeah, that's kind of sucks, but anyway. Okay, so Control A, Control C. But I'm not even using Sublime. I'm using Visual Code. Hmm?
Just like the activate button.
Active. Ah, yeah, that's true. Yeah, okay, well, there you go. Super nice triangles, but anyway, those are triangles.
Yes.
Yeah, sure.
What made you decide to make a response to that resolution?
Well, good question. Actually, it's not important because the formula that it's going through the first line and getting new values as the vertex ID is growing. So as long as the texture is big enough,
Right.
it's good enough. You know. So it's way too big, actually.
Just using 2000.
Well, yeah, exactly. I'm using the 2000 pixel, let's say the first 512 here and then another one. So I could have used just like we can change it actually. It should just be like 3. I think 3 should be enough. If it's 2, it's going to be less. Yeah. Well, oh my God, it's so painful to change.
Do if you need more points than one row, one maximum.
Well, it's going to repeat.
Maximum texture with.
It's going to use this. It's going to use the. Yeah, if I.
Maximum resolution of texture is 16,000.
Yeah, but it's it's like it's still like a lot. You're never gonna. Really?
Really?
It's like 4K by 4K. It's like 16 million
Yeah.
points for your geometry.
No, 16,000.
No. No.
Just one line.
Yeah. Yeah.
Ah, 3 rows.
Yeah. 4K times 4K. It's like 16 million.
You're not limited to just one line. It's structured.
Yeah, exactly.
But you need to calculate how to turn the. Like,
It's like 16 million. So if you have a 16 million points in your SOP, a 4K video is enough.
16 millions, one row?
No. No, you have 4,000 pixels on one row and 4,000 row.
Yeah, but you need to switch rows. Like,
It does
your
that
formula,
automatically.
Yeah, okay.
The position.
Yeah, the formula,
Yeah.
think about it that way. We start one by one until we reach the end of the width. Then we go back one line up and then we continue. So that's how this formula
I
works.
understand the concept.
Yeah. yeah, I'm gonna drop it in. Let's open the toe. I'm gonna drag it inside. So step 1, pose norm UV setup. Okay, now you can drag this image into the network so we can have a look at it. Okay, so that's what we want to do. So imagine the input is our animated SOP. So usually, and the one we want to record, I assume there are triangles. You know, we're not going to record like line SOPs. That would be like slightly different, but here we're recording like SOPs with triangles. So each triangle is going to go through the geometry shader, and each triangle is composed of 3 points. So we need 2 things. The first thing we want to have is for each point, you know, a primitive as a list of vertices. So if, let's say, I create a sphere, if I middle click, I have like 722 points. So, and I also have, well, if I change it, for example, to not primitive or polygon, you know, we can have different numbers for them. So it's always a number of vertices and a number of primitives and how they are joined together. So this is the thing that we want to store, is that if I take this sphere and I create that to sub2, a sub2 that, okay, see that here I have all my points. They all have this vertex ID I was talking about. All the attributes, so we need to store that, the position, the normal, the group, and the other thing we need to have is the primitive information. So I have this list of points, but I'm going to use some of them to build triangles. So those are also index of primitives, but not index of vertices. So here I have like, I don't know, like 200 primitives that are using the vertex number 2 and 1 and 0, 4, 3 and 1, 5. So in order to rebuild the geometry, we need to store that information as well. So the first stage would just be to create that. So I have like, not vertices here. I have like points, which are like 3 numbers. So this can go into every pixel of a top. So, you know, I can have a lot of point position in there. Normals in another one, and UV in another one as well. It could technically store like 3D UVs as well as RGB. Okay, so that's what we want. So the way to do it, I'm gonna go back here. So we're dealing with input triangles as primitives. Then I have access, remember, I have access to the 3 points inside the geometry shader. And the 3 points, I also know their vertex ID. Okay, using this vertex ID, this formula to, you know, translate an ID into a 2D position, we're going to use the same concept. So as we go through vertex ID incrementing, this corresponds to a location in a 2D space. But actually here, it's not a pixel here, because the geometry shader generates, you know, primitives. So we are actually generating quad in the world. But the location where we create this quad is very important, because in the end, we're going to send that to the pixel shader. It's kind of the pixel shader will look at a given location in space. I'm going to draw quads at the right location in there. Okay, so for each point I know its position, I know its UV, I know its normal. So I'm going to create a quad for point A here using this formula to change the ID into the quad location. And we're going to actually draw a quad with the same position UV and normal at each quad corner. Because in the end, it's going to be sent to the pixel shader interpolates. We don't care about interpolation. We just give the same value of each vertex of the quad. Okay, makes sense. And the width here, I call it UV unit just to explain the shader code. What it means, it's the actual physical length of the quad that we want to draw. So we draw those 4 points. So in terms of inputs and outputs of the vertex shader, the geometry shader is taking one triangle, and for each point we'll generate a quad. So one for point B, one for point C. So it's generating like 6 triangles for each input triangle of the SOP. Make sense? So this is how we're basically populating our, let's say the texture. We're drawing inside not the texture, but we are going to render that after into a top. Okay. So yes, after the rasterization that I was talking about, pixel shader will get this information. So for each quad, and this is why it's called a fragment and not the pixel, we created those information like ID, position, UV, and N that are available in the interpolated in the pixel as well. So here we want to have 3 separate textures to store the normal, the UV, it's a bit small here, and the position. So we're going to leverage the multi-buffer rendering of a GLSL top. A pixel shader can write into more than one buffer in a single shader. So we're going to use this to be more efficient. So that's what we want to do. Any questions? Okay, cool. Yeah.
The quads are larger than 1 pixel. Right?
Well, they will be exactly 1 pixel actually. Yeah, yeah. Okay, so let's have a look. So if we go back, what we have here is basically we have our geometry, animated geometry, that is getting in our talks, and we will want to have outputs, tops, that basically represent this data here. So right now, we have not a lot. So here we have a GLSL material. Okay, the GLSL material is rendered this top. So which is a GLSL. It's a it's a render from a camera that actually sees the whole thing. So the little quads that we are drawing, the camera is looking at them, and we're rendering that with this render top. Here, we're actually using 3 color buffers because we're going to use in the pixel shader, we're going to write in the 3 different buffers. So now let's see, I will explain the different stages because we would not have time to write everything here. Here in the vertex shader, we don't do much. We're just passing through the information of the vertex. We are copying the object space position, normal, UV coordinate, and we are adding the vertex ID I was talking about. So it's a vertex attribute with the keyword GL vertex ID that we're copying inside the output structure vertex ID. So flat int just means that flat means I don't want that value to be interpolated later on in the pixel shader. And it's an actual integer. Okay. Here, see the GL position, which is the screen space location of the vertex. We don't really care. You know, we say it's 1, but we're going to recalculate it in the geometry shader anyway. Okay. Then if I look at the other end, well, we're not done yet with that, but the pixel shader will receive an input structure for the fragment that has the object position, the normal and the UV, and then we're going to write, you know, the different values in the different buffers later. Okay, so let's start and let's have a look at the geometry shader now, and open that in a text editor. Okay, so now we have input triangles. That's fine. The output will be also triangles because we're going to draw 3 quads. And 3 quads is like 18 vertices for all the triangles we're going to create. Here again, this is for translating our ID into a 2D location to define where each quad will be drawn. This is the array of data for my input primitive. And the output information that I'm going to send to the pixel shader. I'm just interested in object position normal in UV. So if you have more attributes you want to store as well, they would be added here. So we would transfer more attributes for each vertex and create more to be passed on to the pixel shader. Okay, so now here we are iterating among the 3 points of the input triangle. We are accessing the vertex ID of each of those points. So remember I'm going to make a, let's say, to show the drawing at the same time. Oops. Okay. So here it's the ID 20 of the first point. Then, which is accessed through each point, each of those 3 points. Then we convert that into like the 2D location where we will draw the quad. This, I'm not going to explain the formula again, but it's the width of each quad that we're going to draw. So now what we want to do is this is, remember, we are drawing, basically drawing in screen space. So remember the bottom left corner in screen space is -1, -1. So we start there. And then the more our vertex ID is increasing, the more we're going to draw, you know, on the right and on the top. So this is my bottom left location of my quad. So actually this point here. So now what we want to do is I'm going to create, remember, I'm going to create a point here, but before I emit the point, I need to define what is the world space position, the object space position, UV, and normal before I emit the point. So this is what we are doing here. We have this output vertex we're gonna emit. Okay, so we need to basically, where does it come from? Let's say the object position comes from our input vertices, right? So it comes from this array. So ivert. So it comes from ivert. Then we are generating vertices here. So we are going to use the index here to know for the first point that I'm going to generate, I'm going to look up the first point of the array, the primitive. Then I have access to object position. So let's just use object pos. So we're just basically copying the data that we got from the primitive. So it's the same for the other stuff. So here, normal, yeah. And UV, same stuff. Yes. Do we need to copy the vertex ID? Do we need to pass it to the pixel shader? Exactly. We don't need. Okay. So now, remember that the way we specify where the point is drawn on screen is by specifying the GL position keyword. So in the geometry shader. So the first point of my quad is this point that we built here. See that the important coordinates are the first two ones. Then the third one is the actual depth. We don't care about the depth here, so we say like 0.5 all the time. And last one is for perspective. We don't need it either. So we draw here. We are drawing with this line. With this line, we are drawing this point. Now we want to draw this point, and then emit the primitive. So we create the first half of the quad. So we have to emit like a second vertex, and you will see that overt is a structure that I'm using to emit vertices. Okay, but I don't need to copy those lines again before emitting another vertex. It uses the last values I wrote into object position, normal, and UV. Okay, and here I want to pass the exact same values for each point. So I don't need to copy paste or change the values. But the only thing I need to change before emitting is the position in screen space. So here, what do we need to add to draw this point? Knowing that I have this UV unit that is a vec2. Okay, so it's the dimension, horizontal and vertical dimension of the quad. Well, it still needs to be a vec2. Yeah. And it's called UV unit dot x. And the second one would be 0, right? Because we're drawing right the second point here. So we're just offsetting in uv.x direction. Okay, so now I'll let you find out the position of the third vertex. What should it be? Basically, you want to draw this point here relative to this point. Yeah, basically adding UV unit itself. We can say like vec2 UV unit.x, UV unit.y, but UV unit would be the same. Okay, then we're gonna now, so we have emitted 3 vertices. We're ready to emit a primitive. Okay, so with the infamous bug that I need to copy paste that. Yeah, maybe. So right now, so my render is drawing, nothing. Okay. No, yeah, it worked. I don't know why. Okay. And this is pretty cool. So what we are looking at is like each point, the position is drawn into this. Now there is an interesting thing is this is the render, okay? So there's a camera looking at my, space, but actually right now I have drawn triangles only, but not quads, but it still appears as quads because it's actually, interpolating, or it's like rasterizing. It's rasterizing triangles, and because the triangle is exactly at the let's say the limit of the center of each pixel, it still renders quads.
You lose half of the.
Actually not. If you look here, okay, you actually see those triangles. So it's like even cheaper if we don't emit a second triangle. But just for the sake of it, I don't like to. It's like, but what if, the triangle is not exactly there, then I'm going to lose a pixel. It's going to fuck up everything. So we're going to draw like a second triangle. And remember, by the way, we have one input primitive, and we have a loop with 3 iterations. And in each iteration, we draw the 2 triangles of the quad. So we actually, that's why we take care of the 3 points at the same time. A, B, C are 3 quads. So let's continue here. By uncommenting this, I think you can do it by yourself. So the second one I'm drawing, if I look at the image again, I'm drawing this one. So I start again from there, and I need to draw this one, this one. Yeah, actually the third one is already set up. So the third point is the same basically, it's A3. Second point is just going up UV unit.y. So if we save this, oh yeah, okay, so the first time it works, but the second time I need to copy paste. Okay. Okay, so now we have full quads rendered. Okay. So everyone, it makes sense for everyone. What we just did, it's not magic. Cool. So now we are rendering this. If we look, now we're still missing 2 textures. Let's have a look at the pixel shader. So this is the way we specify in which buffer we are writing. So instead of having just one out vec4, like in all the GLSL top or the shader toy, blah, blah, there's usually just one. Here we're going to use additional buffers for the normals and the UV. Okay, so what this does is write in the first buffer, it writes what we receive in your input rasterized pixel containing the object position here. So now we need to write in the other buffers as well for the normals. So it's a vec4, and we have the information in vvert normal. It's a vec3, so we need to add 1.0. And same for UV. Actually, I should have called it UVs, but and again it's a color, so it's vec4. And we're copying vvert.uv and 1.0, 1.0. Because it's a vec2. So if I write, it should work the first time I save, so I'm gonna save. And here, so this is the render top that actually, is executing this GLSL material, including the pixel shader here. So now I want to render the additional buffers that I wrote. So do you remember what top I should use for that? It's render select. So render select, we use the world pose top that we mentioned. But here we want to have, we want to see not the first. Well, actually by default it's the second one. Yeah. If it was the first one, that would be the exact same position data here. So here we want the normals. So you see, that's the beauty of it. We have like the three information at once. And we see those animated normals also happening. If we have a look at the pixel value, you see those are going between -1 and +1. And if we have a look at here, it's like, well, actually it can go over 1. So it looks good. So let's do another render select and use the third buffer. So those are my UVs. Actually, yeah, I don't like 1.0 here for the UV. Ah, damn it! I need to change it here. Here, let's write 0. Okay, so it looks more like familiar UV because I just put like 1 in the blue channel. Okay, cool. So we have our 3 tops basically that contain, part of the stuff that we need. Actually, it's not the whole thing yet because remember we need the connectivity. Right now it's just a bunch of points. So let's output here. Let's link our render select to our output boxes. And that's it for now. The thing I want to explain as well is this thing. Okay, remember the actual resolution. The resolution of my render represents the maximum number of positions I can store. Okay, so I can make it bigger, smaller. I don't want to be overkill and render like a 4K if I'm just going to use a bunch of pixels. So here the resolution of the render is, for now, it's set to 128 and 63. Basically, it's a division. Okay, it's like we have to decide one fixed dimension. So let's settle with the width. Okay, and then I'm gonna add as many rows as I need if I have more vertices to write. So actually, in the final version, it's not gonna be 128. It's gonna be more than that. It's like 400 something, but doesn't matter. So the resolution, the vertical resolution, is actually our width divided by the maximum number of vertices I decide to be able to store. Okay, and this is actually already set up as part of, this operator. Okay, and ignore those elements here, but it's a max vertices, so 8,000, and we can push it to whatever. It's just going to change the resolution of the render. Okay, so yeah, so that's it for the first step. You can save, and let's go to, let's close this one. Oops, sorry. And let's continue now to handle the connectivity. So let's go to step 3, connectivity out setup. By the way, do you guys want to have like a quick break, or do you want to continue? No? Okay. Yeah, that's why I asked. So let's say like in 10 minutes, okay. And in the meantime, you can ask questions. Cool. Well, let's resume. Let's open this file. So connectivity out setup right there. So remember, that's the thing we are missing. And do I have an example? Yeah. Someone asked the question, really, do we need this connectivity info? Because, we have our vertex indices 1, 2, 3, 2, 3, 4. We can basically guess, how those triangles are formed. But if we look at something, kind of a simple sphere, and look at what the primitives are, and look at the primitives, you see it's not really, there's not really a logic there in terms of number. Like the first one is 2, 2, 1, 0, 3, 4, 3, 1. The other one is, let's say, like 9, 12, 0. So there's no pattern really. We can guess, how to join those points together. So we don't have a choice, but, to store it. Well, we don't need to sort them.
There is no primitive ID.
There is a primitive ID.
So you cannot just use the primitive ID when you
No.
No?
Well,
the primitive ID in different points. Right.
yes. Yeah. Even, consecutive primitive ID is not enough, But let's see how we do that. I just put an example. So it's a different geometry shader because it does not generate 3 quads per each input triangle, but each triangle we need to store its connectivity. Connectivity is 3 information, so a single pixel is enough for that. So we can just draw a 1 pixel width quad, and that would be enough. The only thing that is changing here is we're going to use not the vertex ID, okay, of each primitive in the geometry shader, but we're going to use the primitive ID. That is also something that is accessible, but only within the geometry shader, actually. It does not exist in a vertex shader because vertex shader has vertices as inputs, not primitives. But the geometry shader has primitive as input, so it knows which primitive index it's currently processing. So that's what I illustrated in purple here. The instance ID is 42, but the vertices around it, they have all other vertex indices that are different. It's like 21, 22, 20. Well, this could be like non-consecutive number, like I showed earlier. And the idea is to use the same algorithm to translate this primitive ID into the location of a quad. So we're going, if we have like 10,000 primitives, we're going to go from 1 to 10,000. So we're going to fill this whole space going up. And the actual vertex, the actual quad we're going to draw 4 points. And then the attributes of those points, we're going to create one, which will be called like vertex indices. So the vertex index of the primitive. And we're going to use the same values for the 4 points, remember? Then the pixel shader will see this value, and then it will know for this pixel, I know the ID of A and B and C, and then later on we can rebuild the triangle from that. Make sense? Okay. So let's have a look at, vertex shader is pretty much the same here. Okay, we are passing, well actually, yeah, here we could not pass anything for the vertex. Well, except the vertex ID, of course, but the position normal in UV, we don't care because we're not gonna, store it. So we could remove that. So we're transferring the vertex ID information. And then in the geometry shader, okay, let's have a look here. So as a recap, we receive one triangle and we are creating a quad out. So it's like 6 vertices. Same thing for the record size. Okay, so in terms of what's getting out to the pixel shader is actually just one thing we need is triangle indexes. So those are the index of each vertex in the triangle. It's flat because those are integers, and it's, IVEC because those are integers, and flat because we don't want them to be interpolated before being passed to the pixel shader. Okay. All right, so that's the thing it took me a while to find. It's not the GL primitive ID that we use, it's GL primitive ID in. That's a special keyword only available in the geometry shader that basically represents the thing that I was showing here. It's representing this 42. So I'm processing the triangle with index 42. Okay, same formula again. Same thing for UV unit. There will be the size of the quad we're going to draw. And again, this is the bottom left corner of the quad. So this point right there. We start with this one, then we go to draw a quad. But when emitting, we're going to emit 4 vertices. But before we do so, we need to write the attribute of the point, which are the 3 indexes. Okay, so overt, it's the output vertex. Then remember, we defined this. It's like the 3 numbers of the vertices of my primitive. So it's IVEC 3. So how can I look that up from the input vertices? Remember, this is an array of vertex. So it's in this array, basically, that we need to look at. Okay, but here we are not using a loop here. Why? Because we're not generating 3 quads, we're just generating 1 quad per each primitive. So now I cannot use the index I in there. I need to look in the array myself, and well, I'll let you guess the first one, the second one. So we start with the first vertex in the array. Then we have a look at the data that we want to use here is what? Is the vertex ID. I don't care about the position here. I want to store the connectivity. So I need to have the vertex ID here. So So ID of the first point of the primitive, ID of the second point, and ID of the third point. Okay, so I've written that attribute in my output vertex. Now I'm ready to actually emit a vertex. So first thing, GL position is where I'm going to draw the point to be emitted. So this really looks like what we already did before. It's like this is the bottom left point, so it's fine, it's already at the right location. Then the second one would be this plus an offset, which is defined by UV unit. So first one is a bit to the right and same 8. Okay, then the third one is we use UV unit. And then we have 3 points we emit our primitive. So I guess you understand that I just emit 3 vertices, and they will all have the same values in this attribute. The triangle index will be the same for each point, which I show in this drawing here. Okay, 20, 21, 22, they are the same because this is part of the, the pixel I'm gonna get later. I don't know if it makes sense. The reason why I insist is like, I don't want the value to be interpolated inside the quad eventually. So that's why I repeat the same value on the 4 corners. All right, so let's do then the second part of the quad. So first one, bottom left. Second one is, actually cut this. And we just offset vertically. And the third one is the diagonal. So we add the whole UV unit. Okay. So let's save that. And yeah, first save works. Yeah, got it. So that's the geometry that is using this material. Okay, the geometry is basically a bunch of quads now, and we render that geometry from a camera that fits exactly this. So this is my render, and here, so I'm rendering the geometry. Anti-aliasing, by the way, those you have to disable every single smoothing, interpolation, they're all activated by default, so really have to hunt them. Otherwise, it's, nothing is working. And then now, well, I can have a look at those values eventually. So see, bottom left, oops, is actually the first indexes, like 60, 64, 66, 665, 715. So you see there's not really like a logic in those numbers, but that's way higher number. It looks good, and the alpha is always 0 there. Okay, so now we have this information. It's missing information, so we can have like a fourth output. Here we can create another output. The reason why I always add a number is to control how they are presented on the parent container, because it's not relying on the vertical position here. It's always, it can be messed up. So we call that connectivity and then send that out. And something else I need to explain is, like, remember this here, my record resolution to start the position. Well, I know the number, there's one known, which is the number of vertices, but for the connectivity, it really depends how efficient those points are put together. So it could be, for example, if each point belongs to only one primitive, there's going to be a lot of primitives there and a lot of points. So there's no relationship between the number of points and the number of primitives. So I need, basically what I say is like, okay, let's just make it double, double the size of the number of vertices I will allocate for the connectivity. So here, the actual render, okay, the resolution is 2 times the resolution used for the position and normal and UV textures. So it's like 128 by 63, and this one it's like double the 8. Okay. And again, those need to be in floating point. And well, in this one, I actually, it's fixed in the final version, but we don't need RGBA here because we're just using the first 3 values. So in terms of memory usage, this can be like 32-bit RGB. Same for connectivity, actually. 32-bit RGB. Okay. Any questions regarding this? No? All right. So you can save. We're going to close it and open another one. Now we want to do the opposite. Right? I have those 4 tops and I want to create a SOP out of it. So we're going to build a tool to do that. So let's open like GPU top to SOP. And let's go to the shader setup. Okay, so this image explains, let's go to view, what we want, the algorithm actually. Okay, so remember the very first example I showed was we used a line with 2000 points and it wasn't moving at all. And the SOP itself was static, but we used the geometry shader to move every point of this SOP. Okay, here, it will be the same. In order to be efficient, we cannot rebuild the SOP by animating another SOP. Okay, but we need to start from a SOP because we're going to apply the geometry shader on this SOP. So it must be the most simple static SOP we can find. So as long as this SOP has enough primitives, that the same number of primitive as the SOP we recorded, basically. So as it gets processed by the geometry shader, we're going to use this GL instance ID number to say, okay, I want to reconstruct the primitive with ID 0 or with ID 20 or 40 or 50. And then from all the SOPs, the tops that we recorded, then we can find this information. We can find the connectivity, we can find the position, normal, etc. Okay, so the actual input we're going to use is a static line with as many points as we have stored position into our tops. So this is what I've shown here. This is one of those primitives, so a line segment. And here, actually, we can use also the vertex ID of the first point of the primitive. Basically, we just want something that increments from 0 to number of primitive of my recording. And same for each primitive in, okay, then I need to draw a triangle, right? How I'm going to do it is I'm using the vertex ID, which is 20. Okay, so I need to reconstruct the triangle with index 20. So the first thing we do is look up the index 20 in the connectivity top that we recorded. Then we read the three values inside this, so 40, 33, 63, and 12. And we're going to use those, I need to show the full image here. So the three indexes, like for example, for the point with index 40, well, I need to look at the position in the, the top that stores the position. So using index 40, I use the same formula to know where I should look in this texture. Then I do the same for the vertex index 63 and 12. So it's just a lookup table, basically. So we can grab the right position for this triangle. So once I get the position x, y, z, the normal, the UV, then all this information, I can basically emit three vertices with the right attributes and then write my triangle. So that's what we want to do. Okay. Any questions? Cool. Here, the way it's set up. So let's see. Our inputs are actually our recordings right there. So if we go up, it's actually, again, it's a geometry that's a SOP that is animated. So we see what it looks like, our three pose, norm, UV, and connectivity. So this is the first box that we build together, which is the SOP to top. So it's getting the SOP in, outputting those tops. Now I want to rebuild this exact same geometry in this box. So outputting a SOP. So our inputs are just SOPs. Remember, I need to generate, I need to input a SOP to my material, and this SOP, the number of points, is basically determined by the size of my recording, right? So that's the number of points I have. Okay, and it's static. It doesn't change at all. Okay. So now this material, which is a GLSL material, is using, the vertex, pixel, and geometry shader. So this geometry shader is going to handle every primitive of this line. Okay. Then something else that I wanted to show is a technique that how to build variants of shaders by using DATs and select. For example, now that I have the connectivity information and point location, there's nothing preventing me of drawing triangles or lines or points or whatever I want. I have all the info. It could be a cube at every point of every triangle. It could be anything. So we should not be limited to the output type triangle. It could be something else. So here, the layout, we have like three variants. One for a triangle strip, one for line strip, one for points. It could be billboards as well for each point if we want. Okay, and the switch will just select, the right text depending on the input type that we want to draw. And here, this shader is actually just a merge that will take the layout out plus, the core of the shader here. And this is the shader that's used in the geometry shader. So let's have a look at the core of the geometry shader. Okay, so our inputs are lines, like I was saying. That's the static line we are injecting. We have like two different sizes we need to store, like the size of the tops that store the position, UV, and normal, and the one that is storing the connectivity, because they have actually two different sizes. Sprites parameter we don't use yet. A uniform to control in the geometry shader what kind of geometry or primitive we want to generate. This one I'm going to explain after is special cases where basically we use the same technique, not to rebuild from the connectivity, but just from the position. So if you have, for example, a point cloud or like a Kinect XYZ top, well, you know the connectivity already, because you know like 2 pixels next to each other, or the 3 pixels next to each other define a triangle. I know that, so I don't need to go regenerate those triangles. So that's what this parameter is for. Another cool thing is almost free normal recalculation. So every time we add noise or deform SOPs, we very often have to recompute the normals. And this can be intense on the CPU if you have a lot of points. Here, it's almost free to do. So if we have the input, if we have recorded the normals, then we don't need to recompute them. But if we are deforming, let's say if we are changing our position top and adding noise or stuff like that, our normals will not be valid anymore. So we just recompute them on the fly in the geometry shader. Okay, that's the sampler for the connectivity, sampler for position, normal, and UV. Okay. All right, so the only stuff that we want as inputs for our vertices are the vertex ID, so we're going to use to increment and rebuild every triangle. The camera index is just, it's necessary for like stereo vision. So we don't have a choice but to have that. The output vertex, so here we have to provide those, those are classic information to send to a pixel shader when you convert them from a FONG or from a PBR. And actually it's something that I should explain as well, is that, remember when we generated the shaders from a material, that's what I started from, actually, because I wanted to be able to have the same tweaks as a PBR material. So like a metallic map, all this stuff for lighting. So I just, output that. I'm not going to touch the pixel shader that does all the fancy rendering, but I'm just going to change the vertex and geometry shader to send the right, triangles and rasterization to the pixel shader. So in theory, here you have in the samplers, we have like the base color maps, specular, metallic, and in the uniforms we have the rim, rim color, shadow color, metallic, roughness. So we can still use them when rebuilding the SOP from the tops. We have the same control. Okay, so now let's reopen our geometry shader and continue the explanation. I provided like some utility functions because it's a pain in the ass to write, and we want to do something simple. It's just drawing a point at a given world position with a given normal, with a given color, with a given UV, and for a specific camera index. This takes care of going from world position, or actually object position, into screen position. So you don't have to worry about applying those transformation every time. And at the end, we emit a vertex. Another function that draw triangle, so 3 points, a color, 3 UV, and again a camera index. Here, when using this function, by default, it will calculate the normal from the 3 points that we pass to this function. So it's a free normal calculation. And then it's basically calling the draw point function that we just defined before. And n primitive to close the triangle. This one is we're not going to use now, but if we wanted to draw a billboard, so it's like a kind of a particle. Okay, so just taking a point and creating a quad at this location, you can call this function where it will emit 4 vertices with the size of the billboard that you want. Okay, this other function is the one that I explained, is using an ID that increments to look up into a 2D top to look up the information, because we're going to use this many times. Triangle area is not useful for now. Okay, so this is what it looks like. So remember that it is our input primitives are lines. So here we don't see any loops, right? So we are not iterating through the 4 points of our line. We're just doing something once. And what we are doing is we want to emit 3 vertices and emit a triangle. Okay, so first thing we do is I need to look up the connectivity. So let's see here, that's what we do in this image. So connectivity, this is the ID 20. So ID 20 is this guy, okay, the ivert.vertex ID that is coming from this point. And I looking it up with this function ID to UV inside the connectivity top. So this gives me a UV coordinate to look up here. So next thing is to actually use the texture function into the connectivity top to get the value, the 3 indexes like we see here at this location. So we do texture, and then the round is to take care of any kind of rounding that might happen when we look the texture again. If it's not if it's doing any kind of filtering, then it cannot work. So we have our 3 vertices here. So now here we just initiate arrays to store the vertex position and UVs of my triangle that I will emit. Now this line is, remember that let's say if my line has 2000 primitives, but my recording is only half full, okay? So it's like, in practice, there are only 10,000 triangles to reconstruct. So the rest is like black pixels. If you see what I mean, here, like this, okay? Here I define myself the maximum point size that I can record, but actually I'm using half of it. So for all of those, pixels, I don't want to create a triangle. So this line here is like, if the connectivity information I'm reading is just zeros, it means it doesn't correspond to an actual triangle. I should reconstruct. Okay, so it's like just a condition. So if any of the indexes are not null, that's when we start our loop. We need to emit 3 vertices. Then, okay, what would be the vertex index of the first, what would be the vertex index of each of the points I want to emit? So we have to look at the inputs that we have again. It's like this, okay? No, sorry, it's not this. It's coming from the connectivity. Sorry. Okay, so those are our 3 indexes we want. Okay. So for each point that we want to create, we need to look up here the right index. Okay. So for the first point, I'm going to look the first index. For the second point, second index. Make sense? Okay. Then once I have the vertex index, and again, I'm going to go back to the image. There. Like the vertex index, now I need to find those position and normal and UV here in those other textures. Okay, so I need to take the index 40, which is the first index, and use the ID to UV function again to know where in 2D I should look in the position, normal, and UV textures. So we're calling this again using the vertex index as a parameter. And the second one is the size of the recording. So now I have the UV where to look into those textures. Okay, so now I want to basically read the values using this UV coordinate. Okay, so I have my 3 samplers: post text, UV text, norm text. So for the vertex, I'm going to use the texture function. So the first parameter, as you remember, is the sampler that we want to use. So the sampler for the position is pos text. And the location where we want to read is the one that we just computed on the line above. So it's vertex info lookup. So for the UV, we're going to use the UV text sampler. And the same location, right? Because we are reading in the 3 different textures, but each one of them all the different information. So I'm going to use the same location to read. And finally, for the normals, I'm going to do the same. So I've actually reconstructed, got back the information for every point of the triangle. Okay, now I'm just going to store that information into my array. And that's where we have 2 options. If we want to recompute the normals automatically, okay, so I'm just testing the value of the uniform there. If we don't want to recompute the normals, okay, then I will draw a point. And I will draw a point using the provided normal that I'm actually reading from the top. Okay, but if I don't want to recompute the normal, if I want to recompute the normal, sorry, well, that's when once I have filled this array, okay, of position and UVs, I can use the draw triangle function with the 3 position and the 3 UVs that are stored in this array, and the camera index, and it will recompute the normal automatically in the end. Okay, So remember, draw triangle, we need to end the primitive to really output a triangle, right? Draw triangle already does that. So we are only adding the primitive if we actually emitted our 3 points in the loop here. So that's why we have this line. Yeah, it's for the normal calculation. Yeah, because if you pass in a different order, the normal can be inwards instead of outwards because it's using a cross product. Will be the right direction, but not the right orientation, but not the right direction. Okay, so let's save that. And what is completely amazing is like, there we go. It's pretty cool. The first time I saw that, it was like, shit, yes! So we actually, if we look at it, our input, it's just a line there. We're going through a null, going through a material that will apply our GLSL material, and then, paf, it's just like, outputting triangles, and actually all our normals are smooth. So it's a proof that the recording of the normals is okay. And let's use this open parent parameters there. We have this recompute normal stuff. That was the uniform I was talking about. So if we use this, well, actually you see there's no more smoothing because we are computing for every triangle. But what's cool is like you can pass any kind of crazy position and it will compute the normals for almost no cost. Here, let's see the rest of the shader. Here, remember, we saw like render as. So it's how to tweak our geometry shader to control whether we want to output lines or triangles. It's actually a uniform, which is called render as, which is defined at the very top. So if it's 0, we want triangles. If it's 1, it's lines. If it's 2, it's points. So in our actual geometry shader, we can use conditions to say if it's 0, then this is what we just did, like creating triangles. Okay. Then yes. Otherwise, we have another condition here. If we just want to draw a point, then we don't really care about the connectivity and normals. Well, actually, yes, normals, yes. But it's way simpler. We're just drawing points and using the first vertex ID, the first point of my line, and we just draw a single point. For the lines, it's actually, well, let me see here. Yes. I think, yeah, the only thing that we change if we're drawing lines, it's the output type that will change to be lines. So we can have a look at the end result here. If I change that to lines, I'll just, there's nothing more to do. And also for the points, it's still gonna give a color for those points. But yeah, so it's a very simple way of toggling. And then I could say render as cubes, and for every point I would generate a cube at the point location or a billboard. So actually I'm gonna show an example with all of those settings, and you can eventually reuse for your project if you want. So those maps are just the maps from the PBR material that are just exposed here, so we can drag tops to apply. Okay. So in the end, the out is actually, you know, and that's something I want to explain here, is like technically, it's not really a SOP. It's a SOP that went through a material, you know, to be drawn. So if you add more SOP operators after, it's not going to do anything, actually, because it's not. It's kind of a trick that I use to output. The reason why I output a SOP is because you can feed that into a geometry after, and then you can draw multiple instances, rotate them, etc. But it's not really a SOP. It's a SOP on GPU. It's weird, but this is what it is. So if you want to transform this SOP, well, you don't have a choice but to either play with the tops that we feed to this container, or actually edit the geometry shader itself. So, you know, if we look at the geometry shader, okay, and then I want to make every triangle of the geometry shrink randomly, well, I'm going to work inside the geometry shader. Here, I'm going to expose like a new sampler that will be my top, okay, the top that is controlling the effect. And then I'm going to use the vertex ID or the vertex UV to actually look up a value in those tops. You know, it's like the whiter it is, the bigger the triangle will be. And then that's how you work. So you work inside this framework and not, you know, adding SOP operators after. Does that make sense? Okay. Cool. So, yeah. So now if we look at the whole thing, is like we have this SOP that is getting into this top generator, and we're streaming that back into this one, and rebuilding the exact same thing on the other end. The banana, I can, you know, drag it in the color map, you know, metallic map, etc. So it behaves like a PBR material. And now the cool thing is, like, in between here, you're in top space. So you remain on the GPU all the time. So you can have like all, you know, 2D shaders, tweaking your position, or tweaking your connectivity, or tweaking your normals the way you want. And it's almost free doing that. Okay, so now, as we don't have much time left, we're not gonna, I'm just gonna present the recorder and the player and explain what kind of workflow you can have with those tools. So right now, you know, those are tops, I stream them, but I would like to store that animation, especially animated SOPs are a pain in the ass to store, you know. You don't want to have like a sequence of OBJ file or a sequence of FBX files or blah, blah. You just want, you know, with this, because it's doing real-time images from animated SOP, there's nothing preventing me of recording that into a movie and then playing that back later and just, you know, have the exact same animation. So let's have a look at how we can do it. So you can close this. And see a SOP recorder, so what it would look like. So let's open that, and let's jump to the final version. Okay, so the flow is having a geometry, a SOP, feeding into the SOP to top. So now I have to deal with those 4 outputs, the connectivity and UV and normal. So the SOP recorder here the challenge here, well, the challenge, not really a challenge, but those output textures are RGB 32 bits. So we need to actually dump that into animations or movies. So we need to pack and pack. I don't know if you use this. Okay, so I can quickly show that, but basically how it works is just define a location for rendering a movie, hit the record button, and turn it off. Then it's going to create, the sub's going to be recorded in this movie file. Or you can also save to an image. So it would be a capture of whatever your SOP is when you hit the button. Because we can also work with images and eventually crossfade, between two two geometries. We don't necessarily always want animated geometries. So the way it works inside is basically joining everything together, okay, with the add tops. So we have like a single file. It's kind of important to have a single file because we need the connectivity to eventually it can change, and that's the beauty of this recorder is your connectivity can change over time. It's still going to be recorded. Okay, it records. If every frame the connectivity changes, it will record it as well. Even if it grows, if your sub grows, it will record it as well. So and that's why it is good to have this connectivity information. So once we have this RGB 32 bits, we need to pack it into an RGB 8 bit, so we can actually record that as a movie. Yes. Okay, so pack is exactly this kind of usages. There's no file format for movie that accepts 32 bits per color. So you cannot save there's the ProRes blah blah blah. It's like 10 bits. That's the most you can do per channel. Here we want 32 bits. There's one image format that does that. Is EXR, sorry, and it's huge. Just one image is like blah. So we want to dump that into a movie file. So we need to go into 8 bits, and that's what pack does. It takes like a 32-bit texture, and then it divides every 32-bit into 4 8-bits next to each other. And that's why it's actually the reason why the default record size horizontally is 420, because it's going to be multiplied by 4, by 3 actually, because it's RGB, to be like 1260, which is just below the maximum size for non-commercial. Because if you run that, it's like, oh, it's not working, blah, blah, blah. So you can push that to 4K and have like super huge textures, but that's the reason why I put it like this, because I guess some of you have non-commercial. So it expands to 1260 by 135. So it's still pretty low, it's okay. Then this pack is fed into a movie file out. And here we want to use animation codec because we don't want to lose any precision. It's very important to have the right connectivity. It's not rounded value, but it could be funny to use a compressed format and have a look at what it looks like when you play it back. And that's what I think is cool about this, is like there's so much experimentation that you can do. It's like, I have no idea what it will look like. And sometimes it's like beautiful. It's like, oh shit, gonna noise this and blah, blah, blah. And then how the fuck did you do that? I don't know, But, you want to work in top space because it's very friendly for sensors. Your sensor data will be, can be an image. And if you have existing assets, most of the times those are tops. So, I think it's really working with SOPs is a pain in the butt to work in subspace, and it's CPU intensive. And yeah, so it's RGBA animation, and that's it. So yeah.
So the preview in the pack viewer sources is
Yeah, it's just the viewer. It's okay.
oh, it's just the viewer, so it doesn't.
Yeah, it doesn't matter. Yeah. It's more when they render. Render is very important to not have an anti-aliasing, or. But for this one, it's okay. And yeah, it looks like it's kind of cool. Like, this visual actually is nice. Okay. So when this guy, well, right now it's not animated, but the other also cool thing is you can just use a file format which is TIFF and not EXR. That would be much smaller in terms of size, and it still works. So it's exactly the same idea. TIFF will store this information of the pack, so it's 8-bit, and it's going to be recompressed after. So if you hit the pulse, it will save your SOP into this image. So we have the option of recording animation or just images. So next stuff now, and we're going to close that, is to do the same from, I want a player of those files. I dump images, movie files. I want a simple way of actually generating those geometries. So let's open the step 2 final. Okay, so SOP recorder. Now SOP player. The SOP player is basically here. You just browse for either a TIFF or MOV file that you have created before. So in this flow, I have just a torus. It could be an animation, so let's just insert like a good old noise. And let's insert like something to recompute the normals. Okay, so the good thing is, I see the data coming here. Then the way it works is just plug the 4 outlets into the recorder. Let's call that Toto2 MOV. So it's going to record in the current folder. So hit record, stop it, and then for my SOP player, I'm just going to open I don't know where it is. Where was it? What's 222? It's step 2 final. Well, 0 set. Yeah. Oh, really? Okay. So yes. So now I've just opened this, and there you go. And if I want to have like multiple instances of that, well, I think you can probably instantiate your geo with a chop. Or you can instantiate for another top eventually. Actually, that's something that I show with the shaders. You can do that, but the trick is we cannot chain another material on top of that, because the SOP has already its material. So, giving a material to this geo would be ignored, basically. It's just the transformation information, and instancing, I think, will work. So yeah, I think in terms of workflow, it's like I didn't play a lot with this approach yet, but I've maybe a couple of stuff I can show you that what kind of possibilities you can have with those tools. So let's have a look at applications. Okay. Yeah, let's open top to sub for Kinect. Okay, so this is the same component that we used before. It's just that, remember the position only stuff I was talking about? There's a scenario where we don't care about the connectivity because we know the connectivity. We know that here, each pixel, represent a position in space. So that's an image that you would get from Kinect top and use, XYZ position RGB cloud. But we know that those two pixels next to each other and the one under define a triangle. So we use that in the shader. I will not, show the actual code, but this is what it does, and it's created a triangle for those points. So if you toggle this option, it will actually don't require the fourth input, which is the connectivity input, in order to generate geometry. So here, yeah, I just plug that into this guy because it's basically an array of position. It's not even a recording that I made, but it's just an array of position. And the output is, basically your point cloud. And here you also have the option like playing with the primitive type, triangle. You can have lines, you can have points, and points are not shaded. Okay, so this is one simple example. Then I have more funky stuff. Another simple one, SOP morphing. I guess you saw that one coming. It's we walk in top space and just interpolate tops. So I have like two geometries. Each one of them outputs tops. Now pretty, very, very small, like 420 by 3. And same for the torus. We just go through a switch for the position, normal, UV, and connectivity. And then we have like a slider that goes interpolate for each of those input textures between one or the other. So if we have a look at, if we view that, we can go from one to the other. And yeah, I think it's more efficient than SOP, cross SOP, because cross SOP will actually recompute the SOP every time you move. So workflow is simple, just use the SOP to top, output two images, and this is how you basically go from one to the other. You only have to be careful about the recording sizes, because as you interpolate, well, it will go from one. If you have two different sizes of connectivity, it will eventually start creating new triangles, because it will those values will start appear. Okay, any questions for this example? No? Okay, let's move on. Movement smoothing. So again, it uses like a Kinect recording to illustrate the technique. Okay, so what I have here is I have like the recording of, as a movie. So this is a packed movie from a Kinect sensor then using the pack to actually unpack it, right, in RGBA, 32 bits. And what I have is, like, it's an example of creating a tool to deal with my position top. And it's an example of dampening the new position. So if I jump into a new point cloud data, instead of jumping to it, it's going to interpolate slowly to it with a specific dump factor. So, you know, the movie actually play it using a specified index that is bound to the slider. So as I choose a different location, so we just show me, you know, different stages of my point cloud, but creating the animation for it automatically because it's just the input top, the position top that I change. Connectivity stays the same. So it's kind of a very cheap, you know, way of going to different stances in a recording. Yeah. So this one, and I want to mention that every top operator is not 32-bit friendly. So if you use, for example, like a add, if you add two 32-bit together, some of them can be negative, some of them positive, and the add by default, it will clamp. So you will lose all the negative values when using this operator. So that's why even here, if we look at how it's done, the dampener, it's a very simple, you know, feedback loop with the GLSL shader. Because the GLSL shader will not clamp anything. And, you know, the stuff is very simple. It's just taking two values and adding 10% of it with 90% of what we had before. Yes. Okay, let's move on. Okay, so this one is a very much more elaborate version of the top to SOP. So I was explaining that you can make it more complex by tweaking the geometry shader itself to generate billboards or lines, cubes, whatever. So this is an example of it, actually. So this one is like, again, a recording. And here you see that I don't have like the noise around. So here it's like this is a, you know, top to SOP on steroid with lots of settings. In the general settings, so it's relying on the geometry shader to do all this stuff. So let's say, displaying only a section of the point cloud is using the technique I shown, like cut out triangles in the geometry shader by using slices. If I don't do that, well, my geometry is more complex, but I can change, I think there, no. Sorry, here. As I push it, then I can see the background on that. What I like about this is really it makes your GPU faster because it's discarding geometry. Other cool thing is render mode. So it's like you have more choice. Like it could be points, and those points can actually use sprites with the function that I shown before. So if you go in the point setting, point sprite is on, and then you can increase the point sprite. And it's basically using the geometry shader to pop like a quad at each point location. Usually it looks better by turning on the transparency and pushing the size here, so you can have something like more like ghostly. Another thing is a cube. So you can actually draw, let's do that, draw cubes for each point. and control in the cube settings. You can control the size of each cube, so you can make like super fat cubes or not. Even, you know, see that I animate the size. It looks like the SOP is animated, but it's not. It's done on the geometry shader, so it's not, you know, costing performance. Another nice application is downsampling. So remember, like, I can consider that each point of my top represents position, but when I read it, I can skip one every 2 pixels. So it's kind of downsampling the array of position. In the shader, instead of going, you know, pixel after pixel, just increment, and in the formula ID to UV, just go further in the input top. And it's with just a slider, you can basically control, you know, how you then sample your, you know, data array, and then start playing with the, you know, the cube sizes. Another, let's go back to mesh and downsampling. The connectivity, we can actually noise how points are joined together. Instead of this one with the neighbor, we'd say, okay, this one with something random around you. And again, it's done in the geometry shader the same way. You can have a look after. We don't have time, but we can randomize a connection and actually scale it, so you can make it like super wide when connecting the triangle points, and you can eventually animate it. So it gives kind of a, let's say, noise-ish look. You can display lines as well, horizontal or vertical. Let's downsample this here and turn off the animate. One last thing is when going to cube, I was explaining the wireframe. So see, it's drawing the wireframe and the cube, but it's a single pass. And you can have a look in the shader, but it's basically computing the distance to the edge when passing vertices to the geometry shader. So, no, sorry, geometry shader computes this and pass this to the pixel shader. So it's actually pixel-generated wireframe, and you can also tweak the width. So see, actually, it's you see that it's pixel-based because it can be blurry, but you can make it bigger or smaller, or eventually just showing the edges and not the center. So that's another application of geometry shaders. And yeah, so this one again is based on the same concept of, you know, see our line here, it's the same stuff, our geo, and our select with what kind of geometry we want to output, and the big ass geometry shader with, you know, all the stuff, the same function that we used before, draw billboard, draw point, and I spare you the details of this one. Okay, let's continue. Let's close this one. Top simulation. I think this one, yeah, I think it's using the webcam. Okay, so here what we do is the end result will be animated like a simulation running on a SOP that will make it like grow mountains and stuff. So it's a grid with the 400 by 400 elements. Then it's going through SOP to top. Then the actual position channel is going through like a deformer, which is like just a simple shader that will use, it's kind of important to explain, that will use two channels, the position and then the UV. Why? Because, for example, if you have like a complex geometry and then you want to use a top to control, let's say, how the 8 map, well, you need to know where each, how to unfold this top to affect the vertices. And the best way to do that is to use the vertex UVs, because that's basically how you control how to apply an image onto your geometry. So that's why we pass the UV, so that for each point, we know where to look in the control texture to get the pixel value. So here, it's basically a feedback, I think, yes. Feedback that will take a position data, UV information, and for each point, we use its UV to look up like a deformation factor, like what's the elevation we should add over time to this point. So it's a very straightforward shader here. I'm not going to comment too much, but there are two elements, one that will reset everything and one that will apply the stuff. So if we apply it, see that this SOP has a lot of vertices, and I can sculpt it this way and pose it, and it's still pretty smooth whether it's animated or not. And this is where this recompute normals is very handy, but we need to make sure it's enabled. Otherwise, if we don't do that, well, I have deformed my geometry, but the normals are not recomputed. But it makes literally no difference on the performance. Okay. Yeah, normally, yes. It's there. Yeah. Yeah, make sure you uncheck pose. Yeah. Okay. In theory, the limit with the limit of recording, I think it's with the non-commercial version will be 800,000 points. So if you want to record more than that, then you have to have a commercial license, because we cannot write a movie that will be, more than 1280 by 720. Okay. So let's close that. Yeah, you could. Okay, intensive recording. Okay, so this is basically the idea of when you use touch to generate visuals, not interactive, but just generate visuals, and it's super slow, it's okay. You can still render that into a movie and then play that back later. So the idea is like, let's do the same for geometries. I can have like a super complex geometry that is super fancy, as long as it will take the time that it will need, I don't care. Just gonna be one frame of a movie. After that, I'm gonna play it back, and it's gonna cost way less. So that's what I want to show here. Is simple example of I have a big ass sphere with a lot of points. Just want to noise it. Okay, it's running on 10 FPS. Okay, well, that's okay. I use like this component. I will make, this is important, I will make the real-time checkbox off. So it will process each frame and not skip any frame. It will take the time that it needs. And then here, just, record this, turn it on, and then stop. Then let's disable this flag, disable the noise here, and check real time again. And for the sub player, I just reload it, and that's it. I have, I run this animation 30 FPS because it's not recomputing anything. Everything is baked. So I think it's really it allows very complex subs, non-interactive complex subs, to be part of a project and stored efficiently, as videos actually. So I kind of like this. I think it's very practical application. Okay. Growing subs. So what I want to highlight here is that, I took that from the snippets. So it's a L system that is generating like a sub that is actually growing over time. Just to explain that the technique that we use is not limited to a fixed connectivity or a fixed number of points in a geometry. And what is kind of cool is to actually see, this sub being fed into this element. You see that it's filling up the different tops from the bottom to the top with as many points as we have here. And for the movie, it doesn't make a difference. It's just like the movie will be bigger from the start. But when actually, when we record that, so let's record that thing. There we go. And here I think it's playing this. You see that, well, I just recorded the beginning and not the whole thing. But it's kind of, it works well. And that's also why having that as a single movie, make sure that you will not read one frame of a movie and not the next frame. Let's say one frame of the position and the next frame of the connectivity. Because you could get like an offset. Don't, because I've seen that when playing movies sometimes there's kind of an offset that goes on. So, there's no chance there is an offset with just a single movie. Okay, so I think that's it. So yeah, I hope you find it useful, and I hope you see do you feel like you can do something with it? Yeah. So feel free to to publish. To put it online. To spread it. I'm not good at that. What I want is to teach. Inspire and that's enough. So you can use whatever you saw for commercial purpose or anything. And yeah, hopefully I would like to open the door of working with subs with the images. So I tried to find practical applications, but I didn't. I feel there is a lot more to explore with this, and maybe you can do impressive stuff with it eventually. So thank you. If you have more questions, we can take some extra time. Otherwise, thank you for being here, and good luck with Dutch.